That's pretty much labels, and then true labels are a thing called labels.
Okay, hi everybody.
Okay.
We're going to talk about efficient models today and speed versus accuracy trade-offs. And so this is pretty relevant to the talk that Sam just gave, where he's talking about deploying the final model that you trained on really low power hardware. How do you make it efficient and fast enough to do that and in real time? We're we have to put it over.
And that changed.
Okay. What's working? Okay, so we're going to talk about how to speed up the process of running your model. It's not just going to be for test time deployment, like what Sam was talking about. We're going to talk about both training time and inference time, and focus on really easy wins for everybody here to speed up both their training and evaluation procedure. We'll briefly talk about some more advanced methods that you can use down the line once you have a model that you're satisfied with. But really, we're going to focus on things that everybody can implement this week or in the coming weeks to improve your experimentation process. And so when you're talking about model efficiency and model speed, really you're talking about an optimization problem. The thing that you're usually constrained the most by is your hardware. So that's your GPU, how much memory your GPU has, how many CPU cores you have, how many GPU cores you have. And then within that constraint, you can start talking about speed and accuracy trade-offs. So you can choose, for example, bigger models that might give you more accuracy at the cost of running slower. And so to revisit the two processes that now you're all very familiar with, first is training. So you have a bunch of data, this data set that you've curated. You want to pass it through your model. There's a forward and backward pass where you're getting a loss at the end and using that to iteratively improve the model. And then during inference, you're talking about just getting the model predictions. So there's no backward pass. You have some data that you may obtain in a batch, like it may be your validation set or your test set, or in the case of the deployment scenarios that Sam was talking about, maybe it's coming in real time. And so so both of these kind of are impacted by the speed of your model and your model pipeline. And you should care about speed for both of them. During training, you care about speed because longer training means that you have to wait longer to know how well your model did with some set of parameters that you gave it. And over the last couple of weeks, we've talked about a lot of different parameter selection that requires experimentation to tell if it helped or hurt your model. So things like hyperparameter selection, different data augmentation strategies, different input transformations, so things like spectrogram generation, maybe there's different settings for doing that. Trying additional input channels in your video, for example. And then overall, every time that you run a model, you want to look into the performance, try to diagnose any failures, and figure out how to iteratively improve it. And so having a faster model lets you do that more quickly. And then during inference, this is kind of the obvious one where once you've developed a model and either you or other users want to use it, the faster that it runs, the quicker you can get through a big data set. Maybe you want to run it on a mobile device, or maybe you want to run it on an edge device in the field. So you have some constraints about how quickly you may need to run your model. And this is going to be hardware dependent as well. It's going to be dependent on whether you can process a big batch of data all at once, or whether you're just going to get one frame of video at a time, and whether or not your end user cares about real-time results. And then so looking back at this diagram, there's really 3 stages here that we can talk about optimizing for speed. The first is the data loading process. So actually the process of reading all your files from a hard drive and getting it to the model is quite compute intensive. Like doing read and write operations from a hard drive takes a long time. And there are a lot of ways that you can speed up this process and see pretty significant improvements in the speed of both training and inference. The second stage is the actual model itself. So there are ways that you can choose more efficient models, that you can modify the model that you have to run faster. And you can also make considerations for the hardware that the model will be running on. And then the third stage is when you actually have the outputs and you're generating either some evaluation metrics or some output for your end user. And in terms of the importance of each of these stages for your own efficiency gains, I would say it's basically the order that they're in here. You're going to get the most bang for your buck by optimizing the data loading. And we're going to go through a few different ways that you can do that. Then there's some additional speedups you can get by optimizing the model and hardware choices, which can have additional pretty significant improvements, but kind of diminishing returns for how complicated they get. And then the third stage, you're probably not doing anything too crazy at the moment. Like maybe if you were writing video to disk after running your model, there are ways that you can optimize that. But for the time being, I think most people here are just looking at evaluation metrics. And so we're really going to focus on the first 2 stages and specifically on some easy wins to speed up both of these stages. So the first is data loading. So what is data loading? It's the process of choosing which data you're going to send to the model. So you have a bunch of data on disk. You can load that in chunks of varying sizes. You can do transformations to the data as it comes in, like resizing the images to be smaller. That includes doing data augmentation, and then grouping all of that together to send to the GPU. And so in that initial diagram I showed, the data loader becomes this arrow between the data on your disk and the model and hardware that are actually going to process the data. And so there's kind of this analogy that's useful for understanding this. If you imagine that you're moving into a nice new clip art house and you have a bunch of boxes that you need to move from your old apartment into this house, you have some model hardware combo, which is represented by a vehicle that you rented or own. How are you most efficiently going to get all the boxes from your old house to your new house through the vehicle that you have? So you have different constraints in terms of how many boxes you can take at a time. You have different speed characteristics of each vehicle. Like you have a sedan, you can move quickly, but only a couple boxes at a time. Versus a semi-truck, you have really high throughput. You could take a lot of boxes all at once, but you'll go really slow. And then the data loader is kind of like the moving crew that you hire to help you move the boxes from the house into the vehicle. And so you.
I love that so much.
Really long.
Wait, how is the model like hardware? Like, what would be an example of a sedan model or a semi-truck model?
The vehicles are more like the hardware. So you have certain constraints on your GPU. Maybe you have a smaller GPU that can only fit a couple gigabytes in memory versus a larger GPU where you can process a big batch of data all at once. So you have some constraints and you need to optimize how you're going to fit all your data in there.
Cool.
And so the data loader kind of becomes that first optimization step where actually in a data loader, they're referred to as worker threads, and we'll talk about that, where you have multiple workers and you want to make sure that you're optimizing for their time. So if you have a big GPU, a big truck, you want a bunch of people that are going to help you put all the boxes in there all at once. But if you just had a small car and 16 people helping you, there would probably be a bottleneck where they would just be waiting around doing nothing. And then so in terms of your data loaders in PyTorch, there are a few parameters that you can tweak even very early on that can help optimize this process. The first is the batch size. And probably most of you have run into this at least a little bit already. In this analogy, it refers to the number of boxes that you send over at once. In your model, it's how many images get processed at the same time in parallel. Then you also have the input size. This is like the dimensions of your images. And so the larger the image, the more space it takes up in memory. There are speed, accuracy trade-offs here. Usually larger images result in better accuracy at the cost of being larger in memory, so you can fit fewer of them in a batch, meaning you have to use smaller batch sizes, and it slows down the process. And we'll talk more about that. And then finally, the number of data loader workers. So the data loader is actually usually running on the CPU. You have a certain number of CPU cores, and so you can have a limited number of data loader threads that are working in parallel to put data from the hard drive onto the GPU, and you can optimize this number. So the first thing is the batch size. And what is batching? It's just loading multiple images at a time onto the GPU. They can be processed all together in parallel. And that's an advantage of using GPUs. That's why most deep learning is done on GPUs, because the hardware is designed for many parallel computations all at once. Whereas CPUs are designed to execute a single task very quickly. GPUs can execute many, many tasks all in parallel. So it really works out for neural networks, which are lots of parallel matrix multiplications, essentially. And so how this affects speed is that by upping your batch size, you can pass more data through the model in the same number of GPU iterations. Typically, the iteration is mostly constant in time. So the more data you can stick in there, the quicker you can get through your data set. This has diminishing returns, and continuing to increase the batch size. It's sometimes bottlenecked by the amount of GPU memory you have. It's often also bottlenecked by the CPU workers reading the data from disk and putting it onto the GPU. So you have a fixed amount of memory on your GPU that you can construct a batch with. And so you need to optimize how you're going to use that memory. So that could be many small images. It can be a few large images. And different combinations of those can get you to the same overall memory requirement. And so by now, probably many of you have seen when you're developing a model in PyTorch, the input is actually 4-dimensional. You have not just the channels of the image and the height and the width, but you also have a batch size channel. So typically it's represented like this, where n is the first dimension and it's the batch size, followed by channels, followed by height, followed by width. And so this is these are parameters you can optimize, and you just have to kind of do this empirically. You need to run the experiments to see how image size affects the performance of your model. Typically, the larger image size does give better accuracy at the expense of going slower, and typically there are kind of a drop-off in improvement after a certain size. And so when you're running these experiments, you can get an idea of speed quite quickly. You start running your model, you get through some portion of an epoch, and you kind of know how quickly it's going through each iteration. But to get an idea of the performance in relation to the input resolution, you do really have to train a full model, evaluate it on your data set, and see how that affects things.
Just I have a question.
Sure.
So for like ResNet, it resizes everything to 224 or whatever the standard number is. So is that the resolution that matters and
Yes.
not your like original resolution?
Correct.
In two ways though, because the original resolution affects the data loading speed. If you have to load in an image that's like 2,500 pixels by, 1,500 pixels, which is like some like camera traps have huge images. And then you're resizing that to 299 by 299, that data loading speed is super slow, and then the resizing is this additional operation. And so often you actually can make things go faster by just resizing your images and saving them at the smaller size. And then just training on that. That actually might really speed up because you're not loading something huge and then resizing it. But you also can change the input image size in a ResNet. Like it doesn't have to be 224.
Yeah.
So you can make it bigger, and then that's adding basically more parameters to the model.
Will batch size affect the accuracy?
Not very much. There are like some complicated ways that it could, but for the most part, it's not something that you should have to worry about. Would you say that's accurate?
Batch size can make models perform better. I definitely see improvements in object detection models with larger batch sizes, but it usually has to do with batch normalization. So like batch norm does not work well with small batches. And so if you have really small batches and you're using batch norm, you can get some really weird effects.
By batch normalization, what do you mean?
So basically it does normalization based on like statistics of the batch at a very sort of meta level. And so if your batch is like 4, then like the statistics of that batch might be quite weird compared to the statistics of the overall data, which can like take you on strange paths and like end up dumping you in like weird local minima that you can't get out of.
It's something you just add to your model. You just say, put batch norm into this model. It does that normalization for you.
Yeah.
Is it like, how do you, I don't know.
It,
Does ResNet just do that, or?
certain models will just come with it baked in as an additional layer, and so it's not really something that you would need to worry about
Yeah.
adding or taking away.
I wouldn't worry about it. You can actually go into the ResNet implementation that you're using, the default, and verify. I'm not sure with the PyTorch ResNet by default if batch norm is turned on or off. Do you know, Sunny?
Batch norm,
Yeah, is that turned on?
Yeah.
Yeah, okay, it's in there.
classical batch norm.
What would be like a, large batch size, a sufficient batch size to, use batch norm?
I mean, I think, again, it's like a strict trade-off between batch size and image input size. So if you have like pre-cropped images and you can run them at 224 or 299 or whatever, 32, 48, 64. But if that doesn't fit in your GPU memory, then you have to go smaller. I often work with things that have small objects, and then for object detection, you use bigger input sizes. So I'll use like an input size like 640 by 640. And then by definition, our batches must be smaller. And yeah, it's just another thing that you can play with in your experimentation.
Would you then take out the batch norm if you have a batch norm in there then, or?
And with 16, like that would be like maybe a batch of 16. I think once you get, it also depends on the structure of the GPUs you're looking at, and that gets a little messy. Like depending on how the GPU is processing information, you just like if it's splitting up the processing and then somehow there's like something weird going on, you want to make sure that. I don't want to get too into the weeds. I think it probably should be fine for all of you, but I think when you're running with a batch size of 1, for example, then batch norm it basically doesn't do anything, but then it's fine. And yeah, I wouldn't worry about it too much.
And that's also something where you can run an experiment with a few different
Yeah.
batch sizes and just empirically compare
Exactly.
how it affects your performance. And so Taiki's question kind of gets at this next slide, which is how do you actually modify this? Most CNNs should allow you to modify the input size, like any off-the-shelf PyTorch model that you're getting should let you do that. The way that you do it in your data set is usually you are doing a resize transform to the input size of the model. And so, for example, this is Benny's code for the camera trap data set. And within the transform, can you guys read that? Kind of. Within the transform of the data set is a resize operation that uses a configuration parameter for image size. And I think in the defaults, it's 224 by 224. So that's a parameter that you can change in your YAML file for some experiment to see how image size affects your training. Batch size is modified in the data loader. So it's actually just a parameter to the default PyTorch data loader. The default is 1. So it's really good to bump that up if you can. And then if you're using other open source code, you're going to have to do sort of the scavenger hunt that we did early on in the summer school. Pretty much any code base should let you change these things. They're very standard things that you need to be able to change in a deep learning model. And so you kind of have to do some digging. Like in the YOLO v5 code, there are command line arguments for batch size and image size that you just pass in when you run the train script. In Open Soundscape, there is a parameter called sample shape in the construction of the model class. And then in the train method is the batch size. So it's not always consistent, and you might have to dig around to figure out how to modify these things. Then there's a few command line utilities that can help you optimize this for your hardware. I think they've been mentioned a couple times in Slack by now. If you're using an NVIDIA GPU, which everybody here is, there's a command line utility called NVIDIA SMI. And if you run that, what pops up is some information about your GPU, including how much memory is being used currently, how much total memory you have. And those are kind of the main things that you would want to look at for this. You can use another Unix utility called watch to stream that. And when you run watch, you supply how many seconds you want it to refresh after. So if you do this command down here, watch -n1 NVIDIA SMI, that's going to automatically call NVIDIA SMI every second. And so what you can do is open 2 terminal windows. In one of them, you run watch NVIDIA SMI. And so that's going to allow you to, in real time, monitor how much memory is being used. And then in your other terminal window, you can launch your training or inference jobs with different image size and batch size configurations. And you can see how much memory is being used. And so, for example, I ran this on the machine that you guys are all using on Azure or AWS with the defaults from our camera trap classifier code. And it's probably a little bit hard to read, but only 5 gigs out of the 15 gigs of memory were being utilized. So by tweaking those parameters a little bit, you can get higher utilization and should see some speed up pretty easily. If you hit a CUDA out of memory error, that's okay. That just means you've gone too far and you should back up and reduce the batch size.
For the image size.
Or the image size, yeah.
Like, on the other, like, what should we be looking at in this array of a bunch of numbers and things? Like, what do I care about in that chart?
Sure, so in this NVIDIA SMI call, this one right here is the main one.
Cool.
It's gonna be your used GPU memory out of the total GPU memory.
So if you're running a model, that should go up.
How far have you gone in batch size with an image size, the default image size that we have, which is 220 times 200?
I don't remember. I think maybe 32 blue. No, that's not true. I don't remember.
Okay.
You should just try some stuff.
Hey Benny, do you know how big with a ResNet 50 224 image size on a V100, how big can you go with batch size?
No, I don't know.
No,
Go fairly low.
it should, 32 should fit,
Easy.
and maybe 64.
Oh, I think maybe.
Yeah.
512.
512?
Yeah.
I never train with small image inputs, so I like genuinely have no idea.
Tiana, I'm doing 128 with that.
128?
Yeah.
I'm doing 32, okay, so I think I.
You can
Yeah, okay.
pop that guy up. Yeah, take it.
Yeah, I was gonna say, I'm doing 128 and I've looked at NVIDIA SMI and it's like around 70 to 80% of the RAM usage, so that's like near the top.
How is that different from the, when you do, what is it, like H top or NV top or whatever, and it shows you like the percentages?
Top typically shows you the CPU threads.
Okay.
NVIDIA SMI is specifically for the GPU utilization.
So
Okay.
one thing you can see sometimes is like your top will be showing like 100% utilization, but then your NVIDIA SMI will show like 20% utilization. And then it's like you're just getting the data to the model is the bottleneck, basically.
Yeah.
It's like you're waiting for the data to fill in the batch before you can run the batch through the thing.
Okay, cause like the CP, so that percentage is not, it's supposed to be low then, if you're running a model, or?
It sort of depends. Like in general, you want to use, you kind of want to use as much of your memory as you can, but there's diminishing returns. And the diminishing returns start to kick in once like your data loader workers can no longer fill up the giant batch size quick enough.
So if the percentage in the CPUs like isn't being used a lot, like increase the batch size then?
Oh, for the CPU workers.
It's basically, you want to maximize the GPU utilization. And
Yeah, but isn't the CPU what's loading the data?
yes, but so check the GPU first, and if like, and then if you change your batch size and your GPU utilization isn't going up, you can check your CPU utilization and see if that's actually a bottleneck. Like if it's like your CPU is working like very close to completely at utilization and your GPU is still like kind of slow or like sort of like waiting, then that's a bit of a signal that the loading stuff in is taking is the bottleneck for you. But sometimes there's just no way around it. Like sometimes if the data pre-processing, for example, if it's like, I don't know, processing soundscape files, or if you have input images that are 2,500 pixels at a side and you're trying to load them in and then resize them, like that actually could just be a bottleneck that you can't get over unless you like change something about the data that you're loading in.
In the next couple slides, I'm gonna get into a little more about how to like bump up the CPU usage too, if you're finding that's the bottleneck. So these past few slides have really just been about batch size and image size. There's that third component of the data loader workers. And maybe before I move on, if there's any other questions.
Yeah, before we move on from batch, I just increased it to 180 to 128, and it just improved by 4 seconds per, is that
Yeah.
good?
Nice.
Where are you getting the time? Where does the time show?
When it, here in the, like, to the right, that's the maximum time.
TTDN progress bar chosen time.
We're also going to talk about ways to time the different components so you can run these experiments and measure how much they're helping. Okay. The next thing you can optimize is the data loader workers. These are kind of, as we talked about, they're CPU threads that are in parallel moving data from your hard drive to the GPU. The optimal number is going to depend on your data, on your hardware, and the hardware includes both the CPU and the GPU. And the question really is whether the model is waiting for the data, meaning your model is running faster than your data loaders can load the data, or is it the other way around, that your data loaders are waiting for the model to finish an iteration through the forward pass and backward pass. And so in practice, the best way to do this is just to run experiments and see how it speeds up your overall pipeline. For a starting point, usually what I do is I just run in Python os.cpu count. That will give you how many CPU cores you have, and it's kind of reasonable to start with that many workers. This could be changed just straight in the PyTorch data loader. And it should be noted that the default is actually 0, which means no independent worker threads by default get spun up to do your data loading. When num workers is 0, the data loading gets done on the main thread. So the same place that you're running Python is actually doing the data loading. So unless you have a very constrained hardware setup, usually you will see speed up by adding more workers.
Do you lose any accuracy?
No.
Okay.
No, this should not affect your accuracy in any way.
So just changing the number of workers?
Yeah. And then so to monitor how much this is actually helping you, there are some Python tools you can use to time the different components of your code. Python has a package called time, which allows you to call this time method, and you get a number that represents the time at which that method was called. I don't know how many of you have seen this Unix time since epic before, but basically it's when you call this time method, what you get is the number of seconds that have passed since January 1st, 1970, which is just something some people decided on. But this is still useful because you can call time at the beginning of your for loop, and you can call it again at the end of your for loop, subtract the two values, and you know how many seconds have passed. You have to be careful with this when you're running things on the GPU, because the GPU is running asynchronously from the rest of your code base. So if you're calling time while some stuff is executing on the GPU, you don't actually know if that batch is finished yet. So you can run this torch.cuda.synchronize, which will wait for the computation to finish on the GPU, and then call time. And so I put this little utility method in the GitHub on the CV for Ecology School. It's all just forked from Benny's code for the camera trap classifier, and now we'll have some of these timing utilities built in. And so what you can do now with that, before you start your training loop, you can define some time that you want to track for different components. So if you want to track, for example, here, if you can read it, it's data loader time, model time, and post-processing time. So these are all different stages of that pipeline that I showed in the early slide, and we want to see how long each one takes. And so all you do is keep track of the last time that you called the time function. So will give you a value in seconds. And then every time you finish data loading, you subtract the current time from that previous time and add it to the overall data loader time. And then at the end of your training loop, you'll now have the amount of time that each step took. So running it with the defaults, you get an output that the data loader took 21 seconds, the model took 13 seconds, and the post-processing took 0.1 seconds. So with the defaults, the data loader is really the bottleneck in terms of time.
Is the model time like the overall epochs? You might have already mentioned that, or is it like 1 second for epoch?
This is in one epoch.
Epoch, okay.
Yeah. And so this is all in that GitHub as well, if you want to see how it looks built into the training loop. Okay. So that's all I have for the data loader. Does anybody have any more questions about the data loader?
Is it true that the data needs to be loaded in multiples of 2, like 2 to the power of n?
That is a rule of thumb that people use, but I saw something recently where they actually did a study and it doesn't.
Doesn't matter.
Doesn't
anymore?
matter. You can. Jason's shaking his head, so I think maybe he's.
It's not a requirement.
Oh, okay.
It's a rule of thumb.
Yeah. It's nice because it kind of lets you try, almost orders of magnitude difference and see, like often you can double the batch size and you're still fine. And then if you hit out of memory, you can kind of back it off from there.
I thought it was just for like it being able to divide things equally in parallel, like making the computations easier to split.
Yeah, I think that's why it is a rule of thumb, but I think in practice, it doesn't actually have an effect if you have it on batch size.
I mean, it's also rooted in like how computers are built in general, like the number of CPUs in your machine is gonna be a factor of 2. Like you have 2 cores or 4 cores or 8 cores or 16 cores. You don't ever find a machine very often that's like 13 cores. So that's always just something that you're leveraging against, but also your GPU is also, for the most part, a factor of 2 or somewhere thereabouts. But it's just trying to fill up the amount of workers that you have, the amount of CPUs you have, the amount of GPU space you have. Memory is also roughly in orders of 2, so it's gigabytes, which is a factor of 2, or you have 16 gigabytes. So just a lot of the hardware is just in factors of 2, so it just winds up nicely.
Cool, so now we're going to talk about the second stage of that pipeline. And so this is actually optimizing the model that you've chosen, which includes actually optimizing which model you choose, and then how you can modify that to go faster. The easy wins here are going to be the model size and design. That's going to be the main one. Then there's some additional fancy things you can do now with PyTorch, like mixed precision training that we'll talk about. And then there are some more advanced topics, and Sam today covered a few of them. I'm just going to very briefly revisit them, but the most bang for the buck is going to be just in your model choice and in using this mixed precision. So we've encourage you all to not really think so much about which network you use. But since today we're going to talk about efficient models, I'll give like a very quick overview of what the components of convolutional neural networks actually are, what kinds of design choices get made when you're trying to come up with a more efficient architecture. And so when we say architecture, network, backbone, we're usually talking about the same thing. It's the set of convolutional layers that get you from an image input to a feature vector that's, say, 1,000 features long. And so when people talk about their model choices, it's usually how these convolutional layers are arranged. They usually give the network a name like VGG, and then they append the depth of the network onto the end of that. So this is a VGG 16. All that means is that the visual geometry group at University of Oxford designed this thing, and they named it after themselves. And it has 16 layers. So there could also be a VGG 32 with 32 layers. And so what are these convolutional layers? I don't know how much you all have seen things like this. This is what a single convolutional filter does. This thing in the middle is the filter. It's a really simple example of a 3x3 kernel. And what a convolution is you run this filter over the entire input image. So in this case, this is a 5x5 example input. You're sliding this filter over the entire thing. In each cell, you multiply the filter times the input value, and then you sum them all up. And that summed value gets you your output. And so the way that this particular filter is designed, you actually end up reducing the size of your representation. So you have a 5x5 input, and because of the way the kernel moves across the input, you wind up with a 3x3 output. Does that make sense?
And the convolutional layers were really like this idea of using convolutions is really something that came in for images. And it's because it does preserve some spatial relevance, right? So like that top left value is related to the top left region of that image. So like you maintain spatial structure.
And since we're going to be talking about design choices, I just wanted to throw actually the terminology in here. So I already said kernel size, that's how you refer to the size of the convolutional filter. The input size is intuitive, and then when you talk about sliding the kernel across the input, there's this idea of stride. And so in this case, the stride is 1. And what that means is you're moving it one cell at a time and doing a computation each time. You could have a bigger stride. Like here, we have a stride of 2. This is a slightly different visualization. So the filter itself is the dark patch that's moving around on the bigger patch. And then, so the input is the large 5x5, and the output is now a 2x2. Because you've got a stride of 2, so it's only doing 4 total computations. Similarly, you can design this to not reduce the input and output size at all. One way that you can do that is by adding padding around the outside of the input, and then keeping the stride set to 1. And so there's a lot of different design choices around how you actually implement this kind of stuff that are maybe beyond the scope of this talk, but just so you know that there are different ways that you can design these things, and they all have different computational complexity and different effects on the accuracy as well. And then so within a convolutional layer of a network, so like a VGG16 has 16 layers. Each of those layers actually has more than one filter. So you can have many filters at the same spot in the network, and they all can learn different things. Yes.
Sorry, can I just ask, are the filter values determined by your data, or are they just like standardized values?
The filter values are learned during
Okay.
training.
That's what we're learning.
So they're randomly initialized, or maybe they're initialized for some pre-training, and then at every training step, you update them to get slightly better on your data. Right, so then one layer can have actually many filters, and maybe you all have seen like visualizations of what happens when you put an image through a convolutional neural network. And you see in these early layers, it starts to learn edges, and then it starts to learn corners. So let's say in that first layer, if it's starting to learn edges and you have 128 filters, each of those filters can kind of start to learn differently oriented edges. And this is not something that you hard code into the model. It kind of learns it itself to be more useful for its own, for whatever the end task is.
Way back in the day, we used to hard code these. That we would use like handcrafted convolutional filters. So yeah, no, we don't do that anymore.
And then other components that you might see if you look up these model designs are nonlinearities. So things like ReLU. Basically, if you have a bunch of matrix multiplications back to back, they're all linear operations, so they could all just be concatenated into one big one. And so if you add in these nonlinearities, it just helps with the learning a lot more. And then pooling is something else that you might see. And pooling is just a way of reducing the spatial dimensions without doing convolution. So the simplest way is you just average the cells in some region to shrink it down. It's like a downsampling operation. And this is like a very, very brief overview where I'm skipping a lot of details. Stanford has an amazing online class called 231N that's convolutional neural networks for visual recognition. If you're interested in these things, check it out. They have a great overview on the website, all for free. And then so in terms of more terminology that you could get from this that we'll talk about on the next slide, the spatial resolution is a parameter that you can tweak that we talked about in the data loader step. So that's like how big are the things that you feed into the model that has a height and width. It's a little bit confusing, but when people talk about the size of convolutional neural networks, they also sometimes refer to the number of filters as the width. And then so going back to this diagram of the VGG16, For the input image, we have spatial dimensions of 224 by 224 with 3 channels. And then after these first layers, we now have 224 by 224 times 64 filters. And so when you see these like groups of 3 numbers, it's usually the spatial dimensions followed by the number of filters in that layer. And so typically what happens is you progressively reduce the spatial dimensions while increasing the filter dimension. And then by the time you're near the end of the network, you're down to 7 by 7 spatial resolution with like 512 different convolutional filters in that layer.
Is the number of filters different than the number of layers in the
Yes.
network?
So the network depth is the number of layers. So this entire thing, you would say the depth is 16.
Okay.
And that was also indicated by it being called a VGG 16.
But the number of filters increases as you go through these layers.
Exactly. The number of filters is dependent on the layer. So at each layer, you would have some number of filters.
Is this something you can tweak in the model in the code?
It is.
It is, but you shouldn't.
Okay.
Like basically, like these things have been somewhat like optimized by the computer vision community over years. There are a ton of people working on architecture optimization all the time. It is an endless rabbit hole, and you will not make changes that will make
That will
your model better.
Okay.
You could just try different architectures.
Okay, so
You should not touch this stuff. I would not recommend
but
it.
it might make a difference when we're choosing which architecture.
Yeah, you can look at the different architectures, and so basically, like, see all these like 224 by 224 by 3, like
Yeah.
et cetera, like you can calculate, or you can actually usually look up the number of parameters in a model, which is basically just through that entire thing, how many like numbers are getting learned. And if there are more numbers that need to get learned, you can assume that it's going to be a bigger model and be more expensive, like slower to train.
Y'all are asking good questions because you're always like one slide ahead.
I'm so sorry.
That's where we're going. No, that's good. That's good.
This might be a bit of a naive question, but in terms of, you have like ResNet 18, which has 18 convolutional layers, and then you have like ResNet 50.
Yep.
What is the benefit of having, like, when you have 18 versus 50, is the biggest benefit that the computer has more time to look at the images that you're inputting into it, or what is the benefit of having additional convolutional layers?
So it has more parameters.
Sure.
So you could extract more complex patterns.
Sure.
So let's say you have 1,000 different classes and you have very few parameters. It's going to be hard for you to learn actually which features differentiate between so many different classes.
Okay.
If you keep adding more and more parameters, you can learn more complex feature representation.
So if you have like a ton of classes, it's like best then to start with a model that like has more layers because of the complexity, or do you still start simple?
I mean, I would recommend still starting simple because even these simple methods like the ResNet 50 has like 25 million parameters.
So like just, it's okay.
Wait,
So-
does it make sense to change the model as you, like, once you're training your model? Does it make, like, you would change it only if it's absolutely crap or?
So like you can basically like if you try like a ResNet 18, like the smallest possible thing, and you're like, it doesn't, like, I don't know if it's learning. One of the simple things you can try is just swapping out that architecture for a bigger backbone and see if it makes a big difference in performance. If it doesn't, then it's probably something else that's the culprit.
Okay, thanks.
And so really the reason that I brought all this up is so that I can show you this diagram from the Efficient Net paper. Maybe you guys have heard about efficient nets. It was this study that was done about how do we choose the optimum value of spatial resolution, network width, and network depth for some compute constraints such that you can get the highest accuracy. And this is because the most effective way that you can really get a more efficient model, if you're going to start tweaking the model, is just to size it up or down. And so that includes with the input size in terms of your image size, but also in terms of the depth. And so when you're selecting like a ResNet 18 or a ResNet 50 or an efficient net, whatever, they've got some built-in parameters for how deep it is, how wide it is, and probably a recommended spatial input as well. And so they did a study that showed how the width, depth, and resolution of the models affected the classification accuracy on ImageNet. And they varied each of these independently. And for all of them, it's like a similar pattern. You definitely get improvements early on when you're going from very small to a little bigger, and it kind of saturates. And so if you're reading papers trying to decide what model to use, you're going to run into a lot of plots that look like this. And I'm not showing this plot to say that you should care about this a lot, and definitely not to say that EfficientNet is the best model and you should use it, because it's a couple years old now, and that is a long time in deep learning land. But just to get an idea of what these graphs show, on the x-axis, you usually have some measure of model efficiency. And sometimes that is the number of parameters. Like here, this is the number of parameters in millions. And so you can see the biggest EfficientNet is like 60 million parameters. In order to get, only a 1% improvement over a smaller EfficientNet that has 20 million parameters. So there's really diminishing returns. You could also, on the x-axis, sometimes people will put flops, which is floating point operations. It's similar to the number of parameters. It gets bigger as the model gets bigger. The other way that you might see this is people putting the latency of inference on the x-axis. So in this case, actually smaller on the x-axis is faster. And so the direction of improvement is actually up and to the left, because you get faster and then also better on the y-axis in terms of whatever metric it is that you're evaluating. And so this plot is from the YOLO V5 object detector. And so what they're evaluating is the average precision on COCO. And so it's important to note that things like this are always hardware dependent. So if you see somebody that is claiming 250 frames per second, you need to look at what hardware they're actually running that on, and what batch size they're using. So sometimes it's common to benchmark things with a batch size of just one for fair comparison, where you might need to be running this in real time with video coming in 1 frame at a time. Other times they will use a batch size that's much larger than that. And maybe they're not doing an apples to apples comparison. Maybe they're comparing to somebody else's numbers that was a smaller batch size. So these things you kind of have to take with a grain of salt and make sure you understand what the settings were used when they were evaluating.
Is this in terms of speed comparison or performance of the model?
It's each axis, speed versus performance.
Yeah, so speed is on the x-axis and performance is on the y-axis. So ideally, if you can get closer to 0 on the x-axis, that means your latency goes down. And if you can get higher up on the y-axis, that means your performance goes up. And so the trend that you see with all of these is that the slower you get, the slightly better you get. And depending on your hardware constraints and on your accuracy requirements for your research question, some point on these curves is going to be most optimal for you. Okay, and then if you want to just have a starting point, if you're thinking about trying out a more efficient architecture, this isn't going to be that exciting. I'm just going to recommend basically that you use a ResNet 18 as the backbone with whatever task that you're doing for a start. You could also try out an EfficientNet if you'd like. There's also a family of models called MobileNet that is very related to EfficientNet. Essentially, if you're thinking about changing architectures, it's usually not that exciting. You're just going to downgrade to a smaller one, and it's going to go faster, and it might be slightly less accurate, but there's diminishing returns. So maybe you size it down and you don't see any accuracy loss, and now you've just gotten free speed.
But you have to learn the full script of the new model.
Yes, you have to train the full model. But typically, so if you already have an image classification pipeline, plugging in a new backbone should be really easy.
The trick is that the learning rate might not, like, you can just try a new model, but like, make sure that it's usually good to read the paper and go with their defaults for like learning rate and like hyperparameters, because they've sort of found what's the right realm of that for at least ImageNet. And the optimal ones might still be different for your problem, but if you take the same hyperparameters that you ran, that worked well with ResNet, and you use them for EfficientNet, it might be complete garbage, because just the landscape of that model is very different. So you have to be like a little cautious about doing apples to apples comparison. And remember, like when Eli was saying, like the amount of effort you put in to figure out what's best for this model versus that model. I don't know. In the end, sometimes it's better to put more effort into one model than it is to just try a bunch of different backbones, because usually they're all about the same.
Are these all in PyTorch, or how do we access these models?
I believe these are all in PyTorch. Yeah. So Torch Vision has like a lot of built-in models that you should just be able to use, changing one line of code essentially.
If a model ends up being like good enough so the community adopts it, then usually like the hardcore, like inside PyTorch, they will implement it. So it's actually kind of a nice filter, because you'll see all these papers that are like, my model is so amazing. And then they have like some whole thing. And then they'll have their code that's kind of like one-off code that's like usually not in the best shape. And then, yeah, I mean, I don't think that any of you really should be operating like on the cutting edge of model architectures. Like, I think it's better to like let the community kind of vet them and make sure that they're really sort of worth it. And then you guys kind of take it up when it's been proven out. It's like the people who are doing that proving out have way more compute budget than you.
Yeah.
And honestly, it's potentially just a huge time sink or not much. If you see something like this and you're like, oh, well, this new research code is supposedly a couple % better, you go use the research code, you potentially sink a month of time just trying to actually get it to run on your data. And then maybe it was over optimized for the benchmark data set and doesn't show you any improvement anyway.
Yeah.
I've done that a bunch of times. It's not worth it.
I mean, it's 3 weeks and we're still with one model architecture, trying to make it run.
Yeah.
So the last, like, slightly more advanced topic that I'll cover is converting your models to half precision. So when you represent numbers as floating points in a computer, if you've used, in R, do they have doubles? Do you call everything double, or do you call it float? Okay, well, so by default, the floats in Python are represented with 32 bits. So that means that any number, they have this way that that floating point arithmetic is set up to allocate the like literal binary bits for representing that number. And so it's some number of digits for like what they call the significant. And then the rest are devoted to an exponent. So usually it's some number times 2 to the something. And so that gives you like a certain range that's quite large. But it takes up a lot of space. And sometimes if you're doing like deep learning, maybe you don't need that entire dynamic range to represent all the values that could come in and out of your model. And so what people have found is you can actually get away with using 16-bit floats. And so you lose some of the dynamic range and you lose some of the precision for really, really small values. But they've come up with ways to account for that it is no longer really a problem with some of these built-in PyTorch utilities. What that allows you to do is now every parameter of your model is represented by half as many digits of binary. And so it actually takes up half as much space. And it also, the computations that you do are faster as well, because all the data that runs through the model is now represented as 16-bit floats instead of 32. And so there's this, if you're interested in like what the little tricks were that they did to get it to work, there's this paper called Mixed Precision Training. The fun thing is that it's now built into PyTorch by default. It's called Automatic Mixed Precision, also known as AMP. And so if you'd like to poke around, this is also now in the CV for Ecology School Lecture 12 repository. It's really just 5 lines of boilerplate code. where you wrap your prediction call, so where you pass the data through your model, you wrap that with this torch.autocast. That's going to automatically cast all the data to these 16-bit floats. And then one of the tricks that they do to handle the reduced precision with small values is they actually scale up the loss. And so that's like a kind of complicated thing that you can look at in that paper if you're interested. But basically, you can just add this in very easily to your code, and it increases speed like pretty significantly.
How much?
Like 30%, depending on your model and your data.
And how much accuracy or precision are you losing? Not much.
So you shouldn't really lose much. There are probably cases where you could. With this 16-bit mixed precision, you really shouldn't lose any. And PyTorch has published some numbers about it's like 0.01% maybe.
Like, why would you not use it? If it, like, what is the downside then? Because it seems like, why isn't everyone just using it automatically? Like,
There isn't really a downside. It's nice.
That's historically, that's historic reasons. This is a very new development. GPUs from a couple of years back, they don't even support this.
Yeah, so people just didn't think. Yeah, that's also true. The new GPUs, so the V100s that you are all using, support this. The T4s are like the cheaper NVIDIA GPU that supports this.
But they're, like a P100
Does not.
does not support this, which is like just one iteration back of GPU. So it's just pretty new.
but like, we should all today, like, do this.
Yeah, if you're running into speed
Basically what
issues, yeah. I mean, if you're not running into speed issues, like if your model's training quickly,
I don't know, it's many speed issues.
yeah.
Spectrum suck.
Yeah.
Yeah, and so check out this code because it takes Benny's camera trap classifier training code and it just modifies it very slightly. So it'll all look very familiar how to stick this in there.
But this won't help you if your bottleneck is data loading, for example, right?
Never mind.
That's
lost.
Because like if the bottleneck is getting the data to the model and then the model's already fast, then making the model faster is not going to change the fact that the data loading is slow.
Exactly.
My excitement just decreased a lot.
I'm sorry. I started getting, I was like, oh no, she's gonna think this is gonna help.
I was like, this seems too good to be true.
It is pretty
Of course
amazing.
it is.
And if you're thinking about, deploying a model on the cloud and, now you need to run inference over, let's say, all of the Arctic, and the amount of time you're gonna be paying for that GPU is kind of like the cost. If you can speed up your inference by 30%, you're saving 30% of your GPU costs. So it's definitely like a big money saver. This is what.
And because it's doing this to the input data as well, that means you can often double your batch size because now all your images take up half as much space. So in terms of some more advanced topics that you could look into if you get to the point where you're deploying your production model on edge hardware, Sam covered a couple of these. So you can actually continue to quantize the data. You can go from a 16-bit float down to an 8-bit integer, but it's a lot more complicated to do so. In practice, I've actually never really observed a speed up from this for my own models, but I know that other people have, so it's just very application and hardware dependent. Pruning is an advanced technique where you can basically probe your model for what the most useful connections are. And then for anything that's not really contributing, you can just get rid of those weights and ignore them. I've also not really found this to help me very much in practice once I've done all the other speed ups. So it's these are really like the things that you should do very far in the future if you need to squeeze out like a few extra % speed. Knowledge distillation is another topic where you could use a larger model that you trained to kind of teach a smaller model to extract the same representations. And then just very quickly, I'll talk about how we've used this in practice. This is a project that I've been working on with Suzanne and Sarah. We're counting fish in video. So we're doing object detection and tracking in video. At first, when we built the initial version of our system, it was on an old GPU. It was a K80 that did not support mixed precision. And we were getting around 8 frames per second. We moved to a GPU that did support mixed precision, added the mixed precision, and that got us from 8 to 28 frames per second. We then optimized the workers and squeezed out a few more frames per second. We wrote a custom data loader that read in the video directly. So what we were doing before is we were taking video, writing each individual frame as an image to disk, and then running the detector on the images. You can actually instead create a video data loader that would read the video directly, get rid of that writing to disk step, and that saved us a bunch more time. If anybody runs into that with their data, we can talk more. And then we looked into reducing the model size. So we went to a YOLO V5 large and then to a YOLO V5 medium. We saw no drop in accuracy. And so that has put us at 120 frames per second when we started at 8. From basically only the modifications that I've had in this slideshow. And then if we didn't care about some accuracy loss, this is just going down to even smaller YOLO V5s to bump it up. So thanks. I know we're over time a little bit, so.
Any quick questions? Let's go to lunch.